Professor Belfrost's computer science class is back!
Hi, welcome back to my channel, and today we'll discuss the lesson. We are still haven't finished yet about our last discussion on digital logic because I found out some more materials that is better explaining to you about digital logic, especially for flip-flops. So I added here in this lesson today. So today lesson dedicated mainly for explaining flip-flops. Okay, so let's see if I can make it clear. Okay, so no review. Okay, just go to today's discussion. Okay, so before we enter the discussion on flip-flop, I want to teach you a little about floating point numbers. Maybe I've discussed this a little before, but yeah, floating point notation can be used conveniently to represent both large and also a small fractional mixed number, and this makes the process of arithmetic operations on this number relatively much easier. And floating point representation greatly increases the range of numbers from the smallest to the largest that can be represented using a given number of digits. And it is expressed in the form of n equals m times b raised to the power of e, where m is called the fractional part, it is the significand or the mantissa, e is the integer part called the exponent, and b is the base of the number system or called numeration. And fractional part m is a p-digit number of the form plus minus d point d, okay, so on, with d being an integer between 0 and b minus 1, b is base, okay, inclusively. And if the leading digit of m is an integer, then the number is said to be normalized. Okay, the previous equation can be written in the case of decimal, hexadecimal, and binary respectively. For decimal, it is n equals m times 10 raised to the power of e. Hexadecimal is written as n equals m times 60 raised to the power of e. And binary is n equals m times 2 raised to the power of e. For example, the decimal number of 0.003754 and 3754 will be represented in floating point notation as 3.754 times 10 to the power of minus 4 and 3 times 745 times 10 to the power of 3 respectively. And a hex number 257 ABF can be represented as 2.57 ABF times 16 squared. And in case of normalized binary numbers, that the leading digit, which is the most significant bit, is always 1 and doesn't need to be stored explicitly. Also, while expressing a given mixed binary number as a floating point number, the radix point is still shifted to have the most significant bit immediately to the right of the radix point as 1, and both the mantissa and the exponent can have a positive or negative value. The mixed binary number, for example 110.1011 binary, will be represented in floating point notation as 0.110111 times 2 cube, which is equals 0.110111 exponent raised to the power of plus 0011. Here, the 0.110111 is the mantissa, and the exponent plus 011 implies that the exponent is plus 3, okay? This binary, okay? 011 is equals 3 decimal. And IEEE 754, this is code number, one of the rest in IEEE. Floating point is the most commonly used representation for real numbers on computers, including the Intel-based personal computers, Macintoshes, and most of the Unix platforms. And it specifies four formats for representing floating point numbers, and this include the single precision, double precision, single extended precision, and double extended precision formats. So of the four formats, the single precision and the double precision format is the most commonly used one, and the single extended and the double extended precision format are not common. And here's the basic constituent parts of the single precision format. So you can see there are three basic components, which is sign, exponent, and mantissa. Okay, so 8-bit for exponent and 33-bit for mantissa, 1 for sign, which is in the left one. Okay, so for example, if we want to represent plus 10.35 25 in IEEE 754 format, then the following steps can be used. The first step is to convert the 10.25 in binary, which is equal to 10.10.01 binary. And for step 2, we need to normalize by bringing the decimal point in front of first non-zero bit, which is 1.101 times to the raised to the power of 3. Set 3 now the mantissa is 0101 and exponent is 3, so we need to add 127 to the exponent to get an exponent in excess 127.4, which is 130, which can be represented in binary, which is 100010. And now the representation can be shown can be seen as shown in the figure on the slide. Okay, so that's just a little lesson about the floating point numbers. Maybe there will be another chapter that will discuss a little bit too about floating point numbers. Now let's learn more about logic gates. So as I've told you about in a previous lesson, the logic gate is an electronic circuit which accepts a binary input and produces a binary output, namely 0 and 1. So there are some of them. So first one, the inverter. The inverter or the NOT gate, it has one input and one output, but a logic gate in general accepts one or more inputs and produces one output. And apart from the NOT gate, there are 6 other types of logic gates. So input to a gate will, in this lesson, okay, maybe you'll find another things from another literatures, but we'll stick to this convention, this lesson. It can be designated by binary variables like A, B, C, etc., and the output will be indicated by binary variable Y. In some textbook, the Z or whatever, but I don't mind. Okay, so as stated earlier, that binary variable can take a value of 0 and 1, which are electronically represented by low and high voltage situation. And in terms of Boolean algebra, the function of a logic gate will be represented by a binary expression. First, we'll discuss AND gate. So in this gate, output will be high if both of the input are high, and so both diodes are off. Okay, please please see the figure shown. So such a logic operation is called AND. It's represented by Boolean expression by using dot. Okay. Second is NOT gate. Okay, NOT gate is just inverting. It only have one input. Okay, so one input, one output logic circuit, and the output is the complement of the input. So low input will produce high output, and vice versa. And when interpreted for a positive logic system, a logic 0 of the input produce a logic Y at the output, and vice versa. Okay, so this is called a complementing circuit and inverting circuit. The truth table and the symbol is shown in the slide. The next, oh, I've been done. Okay, so non-operational logic variable x can be denoted as x apostrophe or x with a bar. Actually, there's a bar upper part of the x variable. So that is, if x is the input to a NOT circuit, then the output y is x bar or x apostrophe and read as not x. Okay, so yeah, it has been told before. If x is 0, then y is 1, or it's 1 and y is 0. Okay, so the third one is OR gate. So for OR gate, the output will be high if A or B or both are high. Okay, so we use the symbol plus to then the OR. Okay, so the truth table and the symbol can be seen, as shown in the slide. Okay, number 4 is NAND gate. So NAND gate is actually not AND gate. Okay, so it is an AND gate followed by a NOT gate. It's represented by a symbol as shown in the figure A below. And the truth table is also given below, the figure B. So a small circle in this symbol shows that this is a NOT operation. So actually, a NAND gate is Y equals NOT the ending of A and B together. So it's A dot B together bar or apostrophe. This is complement of the end of A and B. Okay, so it has at least two inputs and one output. Okay, so the fifth type is NOR gate. So actually NOR gate it stands for not R. Okay, so logically a NOR gate is expressed by Y equals not A or B, or A plus B together OR. Okay, so it's just complement of OR. Okay, and the symbol and truth table is shown below, so you can just see it can have more than two inputs too. Okay, now let's discuss a little about the universality of NAND and NOR gate before we step to the next gate, which is XOR and XNOR gate. Okay, so NAND and NOR gates are called the universal logic gates because any logic operation can be realized by using these gates. Consider the figure below, where the input A are, yeah, you see they are interconnected. Okay, so the both of the input is interconnected to A. So we see that the operation will gives us A dot A together complemented, which is A complemented, which is not A. Okay, and similarly we can work this with the NOR gate too, and it also gives us not A. Okay, so let's consider creating an OR circuit by utilizing the NAND gate as shown in the slide. And the truth table can be seen in the figure below, and it's true that this operation results for OR. Okay, so it follows that Y equals A naught dot B naught together complemented, it gives us A plus B, okay, or A on B, okay. And also we can realize it by using NOR gates to as shown in the slide. And yeah, that's also the same thing as before. Okay. Okay, so we have done with the universality of NAND and NOR gates. Now we'll discuss the sixth gate, which is exclusive OR gate, or XOR gate, which is certain form. Okay, so the output of this gate is high only when either of the inputs is high, but not when both inputs are high. Okay, and not both inputs is low. Okay, so the symbol of XOR and its truth table is shown in the slide. I want to pay attention. What is the difference between XOR and OR? Because sometimes it confuses. Okay, and the symbol plus inside a circle is used for XOR equations, and it follows that Y equals A XOR B, which is A plus in a circle, and circle plus B. Okay, so yeah, that's for XOR gate. But we've done because we need to see how we can implement the XOR gate using NAND gates. This is how we can implement using NAND gates. Can you find a way how to implement this with NOR gates? If you can, I will want you to practice that. Okay. So that's about the exclusive OR gate. Next thing is that we have exclusive NOR gate. This is just a complement of the previous XOR gate. Okay, so it's gate complement of XOR gate, and its truth table and symbol is shown in this slide. Okay, so we have done explaining about the basic logic gates. Now we are discussing about flip-flops. Okay, so the basic memory cell is a circuit that stores one bit of information. This one bit memory element is called a flip-flop or a latch, since it latches or locks the data in it. So a flip-flop has two outputs, Q and Q naught. They are always complements of each other. It can exist in two stable states, which is set and reset. So in set state that Q is high and Q naught is low, and reset Q naught is high and Q is low. Okay, so it acts as a memory device. So if it is set state, it will always need to remain set, and if it is in reset state, it also need to always remain reset. Okay, so let's see about the basic NAND latch. Okay, the input are generally designed as SNR, set or reset, and because the NAND inputs must normally be logic 1 to avoid affecting the latching action, and input are considered to be inverted in this circuit. You can see how NAND latch is built as shown in this slide. Okay, so the outputs of any single bit latch or memory are traditional design Q and Q naught. Okay, so in any case, the circuit itself need to have these three characteristics. I want you to read it by yourself. Okay, so to serve the purpose of storing these bits in flip-flops, then two input NAND or NOR gates are used as showing in following figure, and this way we get the SR flip-flop, which is another development of the previous NAND latch. Okay, so SR flip-flop and its truth table can be seen in the slide. So here's the description. I will not read it for you because I want you to take a screenshot and learn it by yourself. It's better. Okay. So this circuit is called SR flip-flop because the input is simply set and reset. Okay. So it's an asynchronous circuit because the output change as it changes as the SR input change. Okay, so if we want the synchronous operation, so a clock pulse need to be introduced to the inputs, as will be discussed. Okay, so uh, we need to learn so another type of SR flip flop with a clock introduced, which is called clock SR flip flop. Okay, and the configuration is shown in this slide. So when the clock is 1, A1 is S0, A2 is R0, the circuit function like the SR flip flop already discussed. But when CK is equal to 0, A1 and 2 is 1, then the circuit reduces to that of a basic memory cell or the NAND latch, and outputs remain unchanged on latch. So here, N1 and 2 from the basic latch, wherever N3 and N4 controls the state of the flip flop. And the truth table, the logic symbol of the SR flip flop are shown. The clock SR flip flop are shown below. Next, we'll discuss the type 6 GK flip flop. So in SR flip flop, there's something that is very disturbing, which is when S and R equals 1, it's not allowed because the output is uncertain. And this uncertainty may cause problems in a digital system. So you need a 1-bit memory cell which has its output and well defined for all possible input combinations. And one of such devices is JK flip flops, okay, with inputs J and K. So let this flip flop, the JK flip flop, have the same truth table as SR flip flop, except for the condition when J and K equals 1. Since Qn plus 1, this is after state, equals Qn 1, 0, and are already occurring in the truth table of the SR flip flop, and let Qn plus 1 equals the complement of the Qn for the new condition, which is when J and K equals 1. So the following table gives you the common truth table of the SR JK flip flops, where there are not allowed conditions, and all conditions are allowed. And this is very helpful. So here's the K-maps with SNR as outputs and taking JK and Qn as inputs are shown. Thus, we have a simple way of designing a JK flip-flop from the SR flip-flop, and the circuit corresponding to K-maps given earlier in is drawn below, which is in the left part, and the right part shows how to simplify the following circuits. Maybe you need to apply Boolean algebra to do this. I want you to practice for this too. And the truth table of the JK flip-flop is given. So the solution that we find the JK flip-flop actually still not perfect. For the level trigger JK flip-flop of above figure, consider the case when JK1, Qn0, and a clock pulse occurs. After a propagation delay f of delta t, which is much less than Tp, which is the pulse width, equal to the delay time of 2 NAND gates, then the output will toggle to Qn1. And since this is feedback through the inputs, then the output can toggle back to Qn equals 0 after another delay of delta t if the clock is still high. Thus, as long as the clock pulse is present, then the output will toggle at every delta t seconds, and this is called the race around condition. And to remove this condition, that we sometimes need to do these things. Okay, the first thing is to make a propagation delay delta t greater than Tp, or the propagation time. The second trick is to pass the output Qn and Qn complement through delay lines before feeding them back to the input. And the third thing is using a JK master slave flip-flop. I'll introduce this third solution in this presentation. So let's discuss JK master slave flip-flop. So this flip-flop is actually made of two SR flip-flops, and the output of the first called the master flip-flop is given to the input of the second called the slave flip-flop, and the output of the slave is fed back to the inputs of the master. And the master is triggered by a positive clock pulse, and the slave is triggered by a negative clock pulse, obtaining by inverting the clock pulse applied to the master. And the circuit of MS flip-flop can be shown in the configuration as shown in the slide. So here, when the clock is high, which is clock equals 1, PR equals 1, and CR equals 1, the master is enabled. And while the slave is disabled as clock complement equals 0. So the master function like a JK flip-flop, and its output occurs at the input SR of the slave. And since the clock is low, then the slave is inactive, and thus Q remains unchanged for the duration of the clock pulse TP. So when the clock goes low, then the state function like an XR flip-flop its output changes to QM, which also appears the input of the master. And since the clock is low, the master is inactive, so that the QM and also S and R remains unchanged as long as the clock remains low. Thus, when the clock is high, then the QM changes according to JK flip-flop logic and is transferred to the Q when the clock goes low, or when it is negative age transition. So here's the truth table showing how this flip-flop work. So next, we have discussed, I think, three of the flip-flops. Now, another types of flip-flop is D flip-flop. So in a D flip-flop, then the output follows the input whenever the flip-flop is triggered, and this can be achieved by means of a JKSR flip-flop. So here's the truth table of the D flip-flop using a JKSR flip-flop. So the circuit is shown below. You need to see that here the output follows the input when the flip-flop is triggered, and if the flip-flop is triggered, the output is the same as the input. This is delayed by one clock pulse. And next about T flip-flop, okay, T actually stand for toggle, okay. So T flip-flop by using JK flip-flop can be developed as shown in the slide, and also it can be used as toggle switch as I shown. Okay, now let's discuss about a shift register. Shift register actually is developed by utilizing the flip-flops we have discussed. Okay, so shift register store as well as manipulate data, and the following figures show how to create a 4-bit shift registers. You see that for JK or SL flip-flop are converted to D flip-flops by giving mutually complementary inputs. And all the 4 flip-flops are triggered by a common clock and can be cleared by giving A0 at the clear input, and during the normal operation then the input is held at 1. So a logic gate is an electronic circuit that accepts a binary input and produces a binary output, namely 0 and 1. So yeah, the input of the non-logic gate has one input and output. Yeah, I think this is has been discussed before, so I skip it. Now we'll discuss about half adder. A half adder is another thing that is very important. So a circuit adds two binary variables, gets a carry but doesn't accept a carry from another circuit or adder. So the truth table is given as shown. Okay. So from the previous slide table, we can develop the equation, the Boolean expression for the sum and the carry as shown. And it can be implemented, the function can be implemented in circuit as shown. And by using NOR gates, we can realize it in this form too. Here S equals S naught, which is as the expression shown in the slide. Okay, so from half adder we can develop full adder. So full adder can add two binary numbers, accept a carry and get a carry. And such a circuit can easily be visualized by means of two halves adder and an OR gate, which is shown in the given figure. Okay, so to synthesize the full adder circuit, then we should proceed from the truth table, and this is given as shown. And from the truth table, we can create this function for the sum and the zeroth carry. And by recognizing that the addition of y repeatedly will also produce y in Boolean expression, and adding ABC twice to the right hand side of previous equation, I can write as shown. And also observing that the addition of the normal and the complement for gets 1, we can get C0 equals BC1 plus AC. Oh, that's I, not 1. Okay, BCI plus ACI plus AB, and the following is really established. And using AND or invert AOI gates, the equation before are implemented in the figure given, which gives the output as and C0. Okay, so now let's discuss a little about combinatorial circuits versus sequential circuit. So the main difference here is that the sequential circuits compute their output based on the input and state, and then the state is updated based on the clock. Whereas the combinatorial logic circuits implement Boolean functions, so they are function only of their inputs and not based on the clocks and the state. Okay, so a sequential circuit use flip-flops, and unlike combinatorial circuit, the sequential circuit has state, which means basically sequential circuit has a memory. And here are some key things to notice. that, like combinatorial logic circuit, a sequential one has inputs and outputs. And unlike combinatorial, a sequential logic uses a clock. Also, there's a box inside the circuit called state. And also, this box contains flip-flops. So it has k flip-flops, and the flip-flop basically store a k-bit number representing the current state. The output is computed based on the inputs with subscript and the state coming out of the state box keyword subscript. And the state may be updated at each positive clock edge. When there's not a positive clock edge, then the state will remain unchanged. And the information needed to update to the state, called next state, comes from the current state, which is the current state of Q, and the input, which is fed through the combinatorial logic and fed back into the state box, telling the state box how to update stuff. Maybe you need to pay attention to the figure below to understand what actually, how actually sequences. So for example, suppose you are currently in state 0, 0, there is an input of 1, then this may produce an input of say 1, 0, and produce feedback that tells the state box to update the state 0, 1 the next clock edge. Okay, so that's actually all of the lesson today. I hope this will help you with the lesson of flip-flops. So here's a little quotes for you. So Buckminster Fuller once said, "You never change things by fighting the existing reality, and to change something, build a new model that makes the existing model obsolete." So that's all today. Thanks. Subscribe, give a like, comment, share this video. I'll always wait for you every Monday. So keep watching and be thoughtful. And don't forget to visit our website, which is scienceweexploresc.unaux.com. I will start for some additional supplementary learning research related to computer science there. Maybe not now, maybe after some weeks. I'm still preparing for it. Okay, and thanks for watching. See you on the next episode. Goodbye.